Welcome to the final section of this class. We're going to end with L'Hopital's rule, which is a pretty cool rule, a pretty good section. I think it's going to be a nice final section for all of you. We'll see if I'm right. We'll see if I'm wrong. Stay tuned. So we're going to start with a nice introductory video about, I'm not even going to mention L'Hopital's rule so much in this video, just going to kind of give some connections to things in the past and show where this thing is going to come from, where this thing that we'll talk about in the next video, this rule, when to actually use it. So most of this section is just a bunch of calculations, evaluating limits. So we're going to need to remember what limits are. Sadly, there aren't a lot of good application problems in this section, so really just is kind of straightforward problems. So shed a tear for that. Let's start by doing a little review. Example 0. Evaluate the following limits. And in part A, I want you to look at the limit as x approaches 2 of x squared minus 9 over x minus 3. So in this problem, remember that limits of rational functions, we can use limit laws, right? Rational functions are continuous everywhere on their domain. So as long as we're in the domain, this is just going to be the same as the function value. We can evaluate it through direct substitution. We can just plug in 2. This is going to just be 2 squared minus 9 all over 2 minus 3. That's going to be 4 minus 9 over negative 1, negative 5 over negative 1, which is positive 5. So as long as a function's continuous at a specific point, evaluating that limit is pretty easy. However, if you remember back from chapter 2, sometimes it's not continuous at that specific point. If we look at this very similar limit, the limit as x goes to 3 of this function, if we try to use direct substitution, all right, if we try to use direct substitution here, what do we get? We get 3 squared minus 9 over 3 minus 3, that's 9 minus 9 or 0, divided by 3 minus 3. This is bad. So this is what's known as an indeterminate form. Okay, and we'll introduce that term a little bit more, not super technically later on in this video, but that's what we have here. So sometimes we'll write it in quotation marks. We'll touch that later. But this is an occasion where we're going to use L'Hopital's rule later on. We also have another way of dealing with something specific like this. We have a way that works in some situations. L'Hopital's rule applies to a much broader class of problems, but right, we could solve this before. We just would factor the top and say, oh, there was a removable discontinuity in this function, and this limit is the same thing as this limit. The functions aren't the same because they have different domains, but the limits are the same, and then we can use direct substitution on this new function and get that the limit is equal to 6. All right, this second function is just the line x plus 3 with a hole in it. This is just the line that looks like this. So the limit at that point is actually the value at the hole. Okay, and later on, this will also we can also use L'Hopital's rule on a problem like this. Let's look at part C. The limit as x goes to 0 from the right, remember one-sided limits, of x raised to the 1 over x power. Can we use direct substitution? Well, if we try direct substitution, we're going to get 0 raised to the 1 over 0. 1 over 0 is kind of like some kind of infinity. That's going to be another indeterminate form that we're going to talk about. All right. Actually, I think, wait, this one is actually, sorry, this one actually I think is 0. Let's modify this example slightly. as x goes to infinity of this. We try to use well, you can't use direct substitution on infinity, but as x gets really big, then we have something like x is going to infinity, but 1 over x is like going to 0. I don't want to write equals, but we have something that kind of looks like this. And that's one of the ones, the more complicated ones that we can't do anything with right now. But eventually, we'll be able to use L'Hopital's rule on this too. So that's another indeterminate form, infinity raised at the 0th power. Because infinity is infinitely big, but if you raise something to the 0th power, then it should be 1. And so let me talk a little bit more about what indeterminate forms are. I'm trying to inspire a lot. Why is this? I'm doing everything in green today. I've done this before. I'm trying to kind of inspire where this is coming from. I'm trying to connect some stuff from before with what we're doing right here. So hang in there with me just a little bit longer. So these things that we're talking about, indeterminate forms, basically what these are when are like conceptual understandings of limits that can be anything. Okay. So when we write it this way, these are called indeterminate forms. And there are more. We'll talk about more of them later on in this section. Indeterminate forms. And can be any number. Right? 0 over 0 doesn't simplify to 1, for example. And in fact, over here, 0 over 0 simplified to 6. Right? This is an indeterminate form. We can't use direct substitution. If we use direct substitution, we get 0 over 0, which is either going to be, well, it's going to be anything. 0 over 0 tells us nothing about the limit. That's an indeterminate form. There's a similar one, infinity over infinity. This is another one up here. There's a bunch. We'll talk more about them later. And that's where L'Hopital's rule is going to come into play. We're going to use L'Hopital's rule on limits that have indeterminate forms. Okay, so again, just some more examples of indeterminate forms. The limit as x goes to 3 of x squared minus 9 over x minus 3, right? This is 0 over 0. We just showed this in the last example. But 0 over 0 in this case is 6. But the limit as x goes to 3 of 2 times x squared minus 9 over x minus 3. It's just the same thing multiplied by 2. It's still 0 over 0. If you try to use direct substitution, it's 0 over 0. It's 12. So, right, both of these are 0 over 0. And the problem is that these indeterminate forms don't tell us anything. Okay, and we're going to have to use other tools. L'Hopital's rule is one of those tools. If we can factor and simplify, that's great. But the reality is a lot of limits are more complicated than that. And that's what this section's all about. A new tool to evaluate more complicated limits. Why is it in chapter 3 instead of chapter 2 where we talked about limits? Because we're using derivatives. Okay, so strap yourselves in. That's how we're going to start the next video. And get your calculus shoes on. I should have calculus shoes. Bye-bye.